I'm Salah Gamizi, PhD researcher from Weekend AP, and today I'm going to host TrustML Scientist Seminar. Before that, allow me to briefly introduce Weekend AP to our valuable guests. The full name of the center is Weekend Center for Advanced Intelligence Projects, AEP. It was founded in 2016 as Research Center for the MEX AEP project, and it conducts Japan's leading AI research. The center is headed by Professor Masashi Sugiyama. AEP aims to enhance AI fundamental technology and research and focus on its real-world applications. It encourages collaboration with various researchers and engineers in related fields across the world. We'd be very grateful if you could visit us in our Nihonbashi office in Tokyo in the near future. So the seminar is recorded, and will be available online on YouTube. But still, reproducing any part of the content is prohibited without the author's permission. And talking about the speakers today, I'm very happy to welcome Ludwig Schmidt, who is going to talk about generalization and the link moving from ImageNet to Lion 5B. And to introduce briefly Professor Schmidt, he is an assistant professor in the Paul G. Allen School of Computer Science and Engineering at the University of Washington. And his research interests revolve around the empirical foundations of machine learning with a focus on dataset, generalization, and large models. His research, recently, his group was working on multimodal languages and contributed to the community by developing, creating OpenClip and the Lion 5B datasets. And his research has received new Horizon Awards, Best Paper Award at ICML and NeurIPS, and he was a Best Paper finalist at CUPR and the Sproul Dissertation Award from MIT. Again, Professor Schmidt, I'm very happy to have you today, and we can switch to your screen.
Cool. Thanks everyone for joining. Thanks a lot for the very nice introduction.
Yes, just for the audience, for the question, feel free to interrupt Professor Schmidt, either by raising your hand or writing your questions in the chat if you prefer. And in any case, we'll cover all the questions.
Indeed, feel free to interrupt me anytime. Cool, so let's get started. A data-centric view and reliable generalization. So this is the Trustworthy ML seminar, so I don't think I have to motivate much that trustworthy machine learning is a very important topic. We are all on board with this. Just to recap quickly, over the past 10 years, we have made tremendous progress in machine learning. It's a super exciting time, continues to be a super exciting time, and we have seen a lot of progress on our machine learning benchmarks. And this is great, and this will lead to a lot of useful applications. But when we make the step from taking machine learning out of our research benchmarks into the real world, we often find that it's hard to make these systems truly reliable. A very famous example of that is self-driving cars. It has taken much longer to make truly autonomous vehicles work reliably in the real world. It's still an ongoing process. And applications in healthcare, robotics, online content moderation, and so on just demand that we can make machine learning truly reliable. So a big question for the community is, how do we do this? And I think at the high level, there are two complementary perspectives on this. So like one route to more reliable machine learning is the sort of like algorithmic route, better training algorithms, loss functions, model architectures, and so on. I think we have seen a lot of nice progress from that side, but this is only sort of like half of the equation. I think there's a second half, and that is better training data, which we usually don't study as much in machine learning. Often the focus is more on the algorithmic side, and we treat the data as something fixed. But so over the past 2 years, working a lot on this area of reliable generalization, I have come to the conclusion that the dataset side is actually super, super crucial, and we need to pay a lot more attention there if we want to make machine learning truly reliable. So what I want to do in the next sort of like 45 to 50 minutes in this talk is convince you of this perspective and tell you a little bit about why the better training data sets are going to be so important going forward. And we're going to do this at a high level in 3 parts in this talk. In the first part of the talk, we're going to start out with an overview of the robustness landscape in computer vision. This is to make sure we are all on the same page with what is even the problem we are studying, how does the previous state of the art look. Then in the second part of the talk, we look in depth at the CLIP model from OpenAI. Because OpenAI's CLIP model made a lot of progress in robust generalization on prior distribution shift challenges that were very, very hard, or seemed very, very hard. And then once we have established CLIP's robustness and looked a bit into how to make it more robust. And the third part of the talk, we'll do a deep dive into how CLIP works to figure out where the robustness comes from. And we will find that all of this is indeed from the training data. Cool. And at any point in the talk, as we just mentioned, if you have any questions, feel free to interrupt me. Always happy to sort of like explain in more detail or follow up on any question. Okay, so let's start with the first part of the talk, the robustness landscape in computer vision. And we are going to do this in the context of ImageNet, which is still my favorite data set in machine learning, has received a ton of attention, has been one of the key drivers of progress. And I think despite the fact that this is now more than 10 years old, I think it is still a very, very good starting point for rigorous experimentation, because we have so many models, so many reference points for comparison in the context of ImageNet. Okay, and of course, everyone knows on the standard ImageNet test set, we have sort of almost reached a performance ceiling. But when you take these ImageNet models and you test them in the real world, they still fail in a variety of ways. And in order to make this sort of like more precise and to start to measure the out-of-distribution performance of ImageNet models, the community over the past few years has built a number of widely used test sets that challenge and stress test the ImageNet models out of distribution. One of them is ImageNet v2. This is one of the projects I did during my postdoc. And then other projects here that have been widely used are the ObjectNet dataset from a group at MIT, the ImageNet Sketch dataset from CMU, and then ImageNet R, which also came from a different group at Berkeley. Cool. And so, of course, this is only sort of like one facet of robustness. As we briefly mentioned during our conversation before the talk started, another very widely studied form of robustness is adversarial examples. Again, I'm sure everyone here is familiar with that, but there are many, many different types of robustness. Adversarial examples, perturbations that arise naturally in videos, image corruptions, like adding Gaussian noise or blur pattern, dataset shift, like ImageNet v2 or ObjectNet, what we just talked about, geometric transformation, like rotating an image or re-rendering it in a certain way. And the list goes on and on and on. Nicholas Cellini still keeps track of all of the papers on adversarial robustness, and this has been a very quickly growing field over the past few years. And for me, working on this in this area at the time, I found this a little bit confusing because there were so many different notions of robustness, and a natural question for me was, how do all of these different robustness notions fit together? And are we actually making progress towards broadly reliable models? Okay, and in order to answer these questions, collaborators and I back at Berkeley, where my postdoc did a large evaluation study of a large number of ImageNet models in many evaluation settings. So like at some level, you can summarize the entire paper by, we have produced this big matrix here. So the matrix has 200 rows, every row is a model, and then 200 columns. Every column corresponds to one evaluation setting. So every cell in this matrix means we have evaluated one model on one data set. And there's a lot in this paper. Today, we are going to use this as a starting point, and we don't have the time to discuss everything in depth. But to give you a sense of what's in this test bed, let's first look at the y-axis here, the model I mentioned. In particular, we're going to categorize the models into 3 distinct categories. The first one is what we call standard models. These are models just trained with a focus on improving ImageNet accuracy. The seminal AlexNet paper, ResNet, VGG, and so on. Then the second category of model is what we call robust models. So these are models that from papers with a specific focus on some form of robustness. So for instance, adversarial training, randomized smoothing, special kinds of data augmentation, filtering layers, and so on. Good. And then the third category of models that's going to be important is models trained on more data. So standard models and robust models are always going to be trained only on ImageNet, but we'll also consider models trained on more data. Good. So these are the different models in the test set. And then what are our distribution shifts on the x-axis? This is going to be ImageNet v2, ObjectNet, ImageNet R, ImageNet Sketch, what we already talked about, ImageNet A, another adversarial test set, then a video robustness test set, obviously adversarial attacks, image corruptions, and so on. Good. And before we look at the sort of like results from this test bed in more detail, we'll need to discuss in a bit more detail first, what do we actually mean by robustness? What is the interesting quantity we should be measuring? And to make this much simpler than the big matrix, let's look at a 2x2 grid. Let's say we have 2 models, model A and model B. Model A gets in distribution accuracy 80%, out of distribution 75. and model B gets 90% in distribution and 77 out of distribution. So which of the two models is more robust? If you just want to deploy the best possible model, the answer is clear. Model B is better, both in distribution and out of distribution. But from the robustness perspective, it's not just the absolute accuracy that matters, but also how large is the drop under distribution shift. And here the interesting thing is that this hypothetical model A only sees a 5% drop, while model B sees a 13 percentage point drop. So something about model A is better in the sense that model A suffers less from distribution shift. And the hope is if we can identify what makes model A more robust, we can combine that with model B and get a model that's both high accuracy and sees a small drop on the distribution shift. Okay, so if this is the idea intuitively, let's see how this plays out in real data. So on the next slide here, I'm going to introduce a plot. We'll go through the step by step because this kind of plot is going to appear over and over in the talk. On the x-axis, we have ImageNet accuracy, standard top 1 accuracy. And on the y-axis, we're going to put accuracy under distribution shift, here ImageNet v2. And then every blue dot here on this graph corresponds to one of our standard ImageNet models, as I mentioned, from AlexNet over VGG, ResNet, DenseNet, and so on, to EfficientNet B7. This was state of the art at the time when we wrote this paper. And there's sort of like two interesting phenomena here. One is all of the models suffer from distribution shift. To orient ourselves, I have put a dashed line at y equals x. So all of the points are below y equals x, which means they have an accuracy drop under distribution shift. The second thing that's interesting is all of the models closely follow a linear trend. And there's a great question why this is. For now, we'll just take this as a given. And we are going to say, okay, we can use this linear trend as a baseline because that way we can evaluate the robustness of a new model with respect to this baseline. So concretely, let's say you give me a new model, it gets ImageNet accuracy 71%. Then out of distribution, just by looking at the baseline, I would expect about 58 percentage points on ImageNet v2. And now if your model gets 58, then I would say, okay, that's a nice model, but nothing new here, follows exactly our baseline. But if your model gets more than 58, I would think like, okay, this is cool, there's something better than the baseline we have so far. So like to make this graphically a bit more precise, what we are interested in is this quantity that we call effective robustness, which is the lift above this red baseline. So this green star here would be a hypothetical model that has effective robustness. Okay, and just to clarify why this is a good goal, we know that humans have perfect effective robustness here in the sense that humans get the same accuracy in distribution and out of distribution. We actually did this experiment with 5 expert human labelers. So if our goal is to reach human level generalization, then we need to move the red line up to the dashed line. Okay, cool. So this is the basic experimental setup. Are there any questions right now about how we are measuring robustness or anything I've said so far? Nope. Okay, cool. Then let's continue. And now we are going to put all 200 models on our plot, not just the 80 standard models. And then we are basically we're getting the following result here, the following plot. And the first reaction here is this looks a lot like what we have just seen. And it's like precise linear baseline, all the points are on or close to this baseline. And this is indeed the right reaction. So the point here is that all of the brown points, the robustness intervention, so model with a robustness intervention, they don't see any gains, they don't see any effective robustness here compared to our baseline. The only models that stand out a little bit above the red line are the green points, some of the green points, which are models trained on more data. I've highlighted a few of them here. On the top right, we have a model from Google trained on 300 million images. This is the JFT 300 million dataset. And then we have a couple of models from Facebook trained on the Instagram 1 billion dataset. And then another model that stands out more in the middle that is trained on all of ImageNet, all of 21,000 images. Sorry, 21,000 class is about 10 million images. Just for reference, ImageNet training set is 1 million images. Okay, so more data helps here, but a little bit. Let's look at the next dataset, because so far everything has been only ImageNet v2. There's a good question, what happens on another out of distribution test set? So let's go to ObjectNet. And ObjectNet overall offers a very similar picture. One important difference is the drop is much larger now. Like the dashed line, y equals x, is now about 40 percentage points above our red line, but we still have a nice clean baseline, the red line, and most of the models are on this red line. The only models that stand out again by a little bit are in the top right, the models trained on more data, the green points. Okay, and we could go on over many more data sets now. Let's just look at two more that I mentioned earlier, ImageNet Sketch and ImageNet R. And there's a bit more variation now. The high-level takeaway is still the same. In the top right, the green points are the models trained on more data, which offer the most reliable generalization here. One interesting phenomenon on ImageNet R and ImageNet Sketch is that some of the models trained with adversarial training, the yellow points here, they are above the red line. They have effective robustness, but in a somewhat unlucky way. So for instance, this rightmost point here among the cluster of 3 yellow points, this is a ResNet 150 trained with adversarial training. The ResNet 150 trained without adversarial training is basically just to the right of it. So what adversarial training does here is effectively move a point to the left, which means you reduce in distribution accuracy, but you're not really improving out of distribution. Okay, so there's an important question. This looks pretty consistent in the world of ImageNet, image classification. What about other computer vision datasets more broadly? So in the interest of time, I can only give you a brief overview here. Other research groups have explored similar phenomena and other problems. For instance, a group from TU Munich has looked at similar kinds of robustness evaluations in the context of MRI reconstruction and found very similar results. In the middle is a plot from a paper that I was involved with, where we looked at 60 pose estimation, which is a task people care about in robotics. And on the right, we have a similar plot from a collaboration between Waymo and Google Brain, where they also found that out of distribution follows a nice linear trend as a function of in-distribution performance. And this doesn't only apply to computer vision tasks, but also applies to NLP tasks. So similar plots here from dataset reproductions we did for the Stanford question answering dataset, a widely used NLP dataset, and overall similar trends. All the models follow a nice linear trend, but under distribution shift, for instance, on the Reddit and Amazon domains, you see a noticeable drop. Okay, and overall, so for the pictures, none of the robustness dimensions help them much here. And people also found this in domain generalization, a closely related line of work. And I'm quoting from the abstract here of this very nice paper, In Search of Lost Domain Generalization. They say, we conduct extensive experiments using domain-bet and find that when carefully implemented, empirical risk minimization shows state-of-the-art performance across all datasets. Okay, so far so good. Similar story in this world also. Empirical risk minimization, just standard training with SGD is a really good baseline. There's more here about why all the models end up on a linear trend. Happy to tell you more about it later. For now, let's go back to our main question. How can we fix these distribution shifts? And if you said the more data models here offer some hope in the sense that they are above the red line, but actually this was a little disencouraging when I saw that in 2020, because you have a 10 to 12 percentage point drop and you use 1,000 times more data in the Instagram data set to get 1 to 2 percentage points above the red line. So if you do sort of like a simple back of the envelope calculation, you would need 10 to the 10 times more data to close this gap. And this is a lot of data. So even in the age of sort of like large-scale machine learning, this seems like a big problem. But fortunately, we were underestimating how much more data can help you. And this is what the second part of the talk is about, how OpenAI with the CLIP model demonstrated how much robustness there's left in large pre-training data sets. Before I go into the second part, are there any questions on the first part of the talk?
I actually have one question.
Just go for it.
It's the fact that the models that have been adversarially trained or obfuscated against adversarial perturbation do not really show any improvement for other types of robustness or generalization.
Yep.
I was a bit surprised because the idea is that models that are adversarially trained focus on the strong features, so the most relevant ones. And I was hoping it could help for other domains.
Yeah, this is a great observation. I honestly, this was my hope as well, right? So back in 2017, 2018, I worked a lot on adversarial robustness. And I think back then, the idea was if we make models more robust to adversarial examples, they will become robust more broadly. And also this will also help on other robustness challenges, like these naturally occurring distribution shifts. And then when we did the ImageNet v2 experiment and we had a good ImageNet distribution shift, we could test it for the first time, but this was it's a pretty clear conclusion here. Adversarial training does not help at all on these naturally occurring distribution shifts, like ImageNet v2, ObjectNet, ImageNet R, ImageNet Sketch. And similar story also on CIFAR 10, right? So we also have a new test set for CIFAR 10 called CIFAR 10.1. And on CIFAR 10.1, you can also run adversarially trained networks. It's actually one of the first things I did. So basically, after we had CIFAR 10.1, I ran the network that Alexander's group and I had trained to be robust to CIFAR 10. It's a very nice network, but from an adversarial robustness perspective, very nice network. But unfortunately, for the CIFAR 10.1 distribution shift, that doesn't give any robustness.
I see.
I think there's something about these real world distribution shift that's just not captured by the L2 or L infinity ball.
I see. Thank you.
Cool. Thanks for the question. Any more questions? No, if not, then let's continue with part 2. And this is going to be a lot more good news. I'm sure everyone has seen this, right? In early 2021, OpenAI released the CLIP models together with DALL-E. And in a variety of ways, this was a super exciting release from them. And one reason why I personally found this CLIP paper so exciting was that it made a ton of progress on these challenging out-of-distribution test sets that we just talked about. So in particular, this is from the OpenAI blog post where they announced CLIP. And the nice thing was that they used exactly our evaluation framework for measuring robustness under natural distribution shift. So what they did in their blog post was they compared a CLIP VITL model, so their best model in the CLIP paper, to an ImageNet trained ResNet 101. And they did this so that on ImageNet, the two models have exactly the same accuracy. And then they look at the out-of-distribution performance. This is exactly what we do with effective robustness, right? In the language of our earlier scatter plots, same ImageNet accuracy means we are on a certain x-axis value in our plot, and then we compare the models on the y-axis to measure effective robustness. And then what the CLIP authors showed is that on ImageNet v2, they get +6, ImageNet R +51, ObjectNet +40, ImageNet Sketch +35, ImageNet Adversarial +74. And this is very, very rare, right? If you work on these ImageNet test sets, you know that getting a small single-digit improvement is already enough for a nice paper. And OpenAI sort of like came out with a large double-digit improvement. So I found this very impressive, and this got me really excited in the CLIP models in order to understand what's going on here. By the way, fun fact, the first author of the CLIP paper is Alec Radford, who is also the first author on the GPT paper, GPT-2. Very smart guy. Okay, but now let's talk a little bit more to build some background. How does CLIP work? Did they train it, and how do we use it for inference? So CLIP is a contrastive image text model. And what does this mean? That means our model consists of two parts. We have a text encoder, a standard transformer model that encodes the captions, image captions, as a vector, as a representation. And we do the same for images, either ConvNet or VIT, vision transformer, that takes an image pixels into this shared embedding space. So every training point is a pair of an image and a corresponding caption. And then we set up the loss function so that image and text are supposed to map closely together if they are from the same data point. Otherwise, they're supposed to map far apart. And then we sort of apply the by now standard large-scale deep learning recipe. We train on a few 100 million images collected from the web on several hundred GPUs for a couple of weeks. And we do this with what was at the time sort of a large-scale model, a ResNet or a VAT with 300 million parameters. Good. So this is training, and this is already nice. But one really cool feature of this architecture is that it supports what we know as zero-shot inference. So you can take a club model and you can use it for a downstream task without explicitly fine-tuning the model, right? Normally, if I pre-train a representation and I want to use it on a downstream task, I need to fine-tune the model because otherwise the model doesn't even know what the classes are. The cool thing is with the text encoder here, we can in principle use a clip representation as a classifier for anything we can describe in natural language. And we do this as follows. If we have the classes plane, car, dog, and bird, we make a text string out of it by saying a photo of a plane, a photo of a car, and so on. And we feed these text strings through the text encoder to get one text embedding per class, okay? And we are going to use these basically as a nearest neighbor classifier. So if you give me an image that I want to classify into plane, car, dog, and bird, I feed the image from my image encoder, and then I take the image embedding and just do nearest neighbor search against my text embeddings, and then I predict the class of the closest text embedding. And that's way we can use the model without explicit fine-tuning. And these super outstanding robustness numbers that we have just seen, they are the result of a zero-shot evaluation. So this is again from the clip paper, their robustness section, x-axis ImageNet, y-axis and distribution shifts. They used our code, our framework. They then pragmatically averaged the robustness numbers over 7 natural distribution shifts, ImageNet v2, ObjectNet, and so on. And then we got the following plot. So the blue line here is the ImageNet trained model baseline, and the orange line are the clip models. And this is just much, much better than anything we've seen before. So much closer to y equals x. We can ignore the purple line. One interesting thing is the red line here. So, okay, overall, there were 2 interesting questions coming out of it. Why is clip so robust? And what's going on with fine-tuning? Because the red line here, this is what you get if you take the orange line, the zero-shot clip models, and you fine-tune them to ImageNet. So you're making progress on the x-axis. Fine-tuning increases accuracy as it should, but you're actually not making any progress on the y-axis out of distribution. If anything, you make things a bit worse. And this is only last layer fine-tuning. If you do end-to-end fine-tuning, you make things a lot worse. You lose a lot of robustness. And this led to an obvious question here. Can we get the best of both worlds? High in-distribution accuracy and high out-of-distribution accuracy with a single model. The clip paper authors raised this, and a couple of papers coming around the same time also pointed out that this was an obvious shortcoming of clip. Cool. And basically, in order to address this, this was around the time I started my group at the University of Washington, we found a very simple solution to this, actually, in the paper Robust Fine-Tuning of Zero-Shot Models. So let's just recap what the problem is. The problem is, if we take a clip model here, the purple star, we fine-tune it, we move to the right, better image accuracy, that's good, but we also move down, lower robustness, that's bad. And how do we fix this? And the fix is very simple in the sense that we just do the following. We take our fine-tuned model, we take our zero-shot model from which we started, and we just interpolate the 2 models in weight space. I take half times the fine-tuned model plus half times the zero-shot model, just take the 2 networks, add them together, done. Then you get the blue point here. And the nice thing is, by varying alpha, we can see what curve do we trace out in a scatter plot. And the nice thing is that this curve basically has this good shape. It first goes up and then left. My expectation would have been this is going to straight interpolate in a direct line, and you don't get this nice best of both worlds behavior. But Mitchell and Gabriel were right here. They suggested this, and yeah, this was in the end a sort of like simple but very effective solution. Cool. So this is just a sketch here to illustrate what's going on. Let's look at real data. So again, x-axis ImageNet, y-axis distribution shifts. Here we have 2 orange marker for 2 kinds of fine-tuning. The diamond is last layer fine-tuning. The square is end-to-end fine-tuning. As I mentioned, square better ImageNet, but larger drop out of distribution. The cool thing is, if you do weight space interpolation on top, it doesn't matter that you lose robustness. Actually, the end-to-end fine-tuned model plus YSFT weight space interpolation on top gives you really nice gains, the 5 to 9 percentage points, depending on what you use as reference point. And this works again on a wide range of other data sets. The talk is ImageNet centric because this is where we have done the most experiments, but we also tested this on SIFR 10, works well as well there. We tested this on wilds to give state-of-the-art accuracy on wilds benchmark from Stanford. And after we saw this, oh, this is a super nice trick. Why stop at 2 models? You can interpolate many models in principle. You don't have to pay the sort of like inference time compute of normal ensembling. And this is what we did in the model soups paper. The idea is a model soup is something where you average many models together. And this led us to the state-of-the-art accuracy on ImageNet. There's a lot more to say here, but this is sort of more a separate talk. The model interpolation story. One cool thing we did with it earlier this year was train the state-of-the-art public clip models. So this is together with Flyon and Stability. We took our code OpenClip for training clip models, and we got it all the way to 80% zero-shot accuracy on ImageNet. So just as a side note here, if you also want to play around with clip models, train your own clip models, you can go to our GitHub repo. The OpenClip code supports training clip models on really 8 to 1,000 GPUs. It scales very nicely. Cool. And again, there's a broader story here, what happens in NLP and so on. We have a paper from late last year where we do similar robustness evaluations, and the story is also in NLP. That sort of like few-shot models, zero-shot and context learning are more reliable than end-to-end fine-tuned models. But for now, we're going to skip over more fine-tuning, and we are going to talk about where the clip robustness comes from. So now we have seen clip is very robust. You can make it more robust by weight space interpolation for fine-tuning. But where does all of the robustness come from to start out with? Before we go into part 3, any questions on part 2?
There is actually questions that I got on the chat. It's about, do you have an explanation of why interpolation works? I guess
it's a really good question. Let's talk about this for a second. Yeah. So why does this interpolation work? So I think of it as 2 components. One is sort of like good old classical ensembling, and the second one is approximating ensembling by weight space interpolating. So we have found that in the instances where weight space ensembling, weight space interpolation works, normal standard output ensembling usually also works. So I think of this weight space interpolation as an approximation to classical output space ensembles, where we can save the inference time cost of using multiple models, right? A downside of an ensemble is now inference becomes more expensive because we have to use multiple models in inference time. With this weight space interpolation trick, you still have only one model that uses inference time. And okay, so there's one part, ensemble. Second part is, why does the weight space interpolation approximate an ensemble? And so if like here the intuition is that this works only when you start out from a pre-trained model. So the idea is that once you have pre-trained the model, fine-tuning usually stays nearby, and it stays sort of like in a basin of the loss landscape that is well behaved. So when you do your fine-tuning, you don't really move out of the local sort of like minimum region, and then interpolating in that region works well. So we make this a bit more concrete in the model soups paper, but sort of like this is the intuition for why ensembling approximates, weight space interpolation approximates ensembling. And maybe one last question here then is like, why does ensembling help with robustness? The one sort of like insight here was the models are wrong in a low confidence way, in the following sense. Like when the models are right, they are right with high confidence. When they are wrong, they make their predictions with lower confidence. And so that since you have 2 models that are trained on different data sets, the pre-trained one and the fine-tuned one, they overall have nice complementary generalization properties. So there are some examples where model A is wrong, model B gets it correct, and vice versa. And when one is wrong, the other one is correct, the bad model doesn't outvote the correct model because the correct model makes its prediction with higher confidence. There's a good question now, where do the confidences come from and so on. Also, like the first order, this is the explanation we currently have.
But I have a follow-up question actually now. So you said that it's the behavior from weight averaging is very similar to ensembling. But if you just run ensembling on the output of these different models, do you get better result than weight averaging, or the same result, or how does it
Pretty much
interact?
the same result. Pretty much the same result. So if you fine tune sort of like very aggressively, for instance, when I say aggressively, I mean if you fine tune with a large step size, then you can intuitively get out of this locally nice region, out of the local basin, and then output ensembling will still work, but weight space interpolation will start to fail because you have moved out of this local region. We actually have a nice sort of like analysis scatter plot in the model soups paper where you look at this in more detail. One axis, performance of ensemble, the other axis, performance of weight space ensemble. And in most cases, it's really close to y equals x. So these two really track each other closely.
I see. Thank you.
Cool. Yeah, all good questions. Cool. If there are no more questions, let's go to part 3. Where does CLIP's robustness come from? And this is now going to be about the following paper. Data determines distributional robustness in contrastive language image pre-training. So this gives the answer already away a little bit. It's the data set. Let's see how we establish this. So basically, before we looked at this paper, there were a number of different hypotheses for why the CLIP models are so robust. One of them was language supervision. In fact, it's the whole point of the CLIP paper, right? They showed a new way of combining image data with text data. And so leading contender for robustness was the added language supervision, because in standard ImageNet supervised learning, we didn't have that. But there were more hypotheses. Another obvious one is the training distribution. For CLIP, we actually don't know exactly what the training set is. For standard ImageNet supervised learning, well, we know exactly it's ImageNet. Then the training set size is also an important difference. CLIP was trained on 400 million images. ImageNet models are normally trained just on 1.2 million images in the 2012 training set. Loss function is a distinguishing factor. CLIP contrastive. Normally standard ImageNet supervised is just sort of like 1 out of k softmax supervised learning. Test time prompting is something you can do with the CLIP models, while you can't do that with your standard ImageNet models. And then finally, model architectures. I mentioned that the best CLIP models are VITs. ImageNet models, most of them are confidence in our testbed. So let's go through each of them one by one. Unfortunately for us in the paper, we already had some knowledge from prior work. So specifically regarding architecture, the original CLIP paper already evaluated both ConvNets and VITs, vision transformers, trained with the CLIP approach. And they all fall on the same line. So on this orange line, we have 4 VITs and 5 ConvNets. And this is sort of like in line with what we have observed before. Like on the blue baseline here in earlier work, we had already demonstrated that vision transformers and ConvNets follow the same linear trend. So the architecture is not behind the improvements in effective robustness. Good. So architecture is out. The next point that was already out from earlier work is actually training set size. So what do I mean by this? Back when we did our large-scale robustness study, and we noticed that some of the models were above the red line, we thought, okay, this is interesting. Some of the models are above the red line. If you train them on more data, what happens if you train on less data? And then we trained on ImageNet subsampled by a factor 2, 4, 8, 16, 32. And then the following interesting thing happened. As we subsampled a ResNet 50 by a factor 2, 4, 8, 16, 32, you move exactly along the red line. So the red line is really a property of the training distribution. It's not a property of your training set size. Okay, that means that if you want to have effective robustness, you can't just draw more samples from the same distribution. So training set size is out. So realistically, the two main contenders were language supervision and training distribution at this point. And in order to tell you more about our experiments there, let's introduce one more data set. And this is YFCC 15 million. I guess some of you already know about this. YFCC stands for Yahoo, Flickr, Creative Commons. This is a data set of 100 million image text pairs. And the OpenAI crew who built CLIP and the CLIP training set, they relied on YFCC for part of their training data set. Specifically, they built a subset of YFCC 15 million, that they put into their overall training pool, and they say in their paper, sorry, we can't release our overall training set, but here's YFCC 15 million. This is a representative sample of our training set. And this is what we then use as a starting point for some of our experiments. And just to check that this is indeed representative, we did the following sort of like calibration experiment. We looked, okay, if we train clip models on YFCC 15 million, do they end up on the same linear trend as the OpenAI clip models? And this is turned out very nicely. The answer is yes. So typical scatterplot, ImageNet versus ImageNet v2. Purple stars are the higher accuracy clip models that OpenAI released. And the black stars here are the lower accuracy open clip models that we trained ourselves on YFCC. So exactly the same linear trend as the higher accuracy clip models. Good. And then what we did, once we had this data set, is the basically following. So before our paper, we had results for standard supervised ImageNet training without language, the top left quadrant, and we could train clip models on YFCC, so contrastive with language on YFCC, the bottom right. But the issue with this is always that you're changing two things at the same time. You're changing the training set from ImageNet to YFCC, and you're changing whether you're using language or not. So in order to disentangle the two, you would like to fill in these missing quadrants. You would like to train on ImageNet with language, and you would like to train on YFCC without language. And this is what we did in our paper, basically make these experiments possible. So let's look at the top right quadrant first, ImageNet captions with clip. So how do we do this? So the ideal experiment here would be if someone just gave you text annotations, the right text annotations for ImageNet. The problem, of course, is ImageNet doesn't have text annotations. It only has these 1 out of K class labels like German Shepherd, Golden Retriever, Bike Helmet, and so on. So there were a couple of ways of potentially getting around this. One was we could use caption templates like a photo of a German Shepherd, a photo of a Golden Retriever, and so on. We could use an image captioning model, but the problem with that is that you introduce a confounder. We could use data collection, in a sense like use mTurk and so on to collect new annotations from human, or the ideal thing would have been get the original text annotations if they exist. And here we sort of like got lucky. We knew ImageNet very well back from the ImageNet v2 reproduction experiment. So we could actually, with a lot of data wrangling, connect 500,000 ImageNet images back to the original Flickr images. And once we had made that connection, we could just use the text captions that people had generated back on Flickr and build an image text data set that way. Okay, you call this image text data set ImageNet captions, because it's ImageNet with captions. Here are a couple examples, like a duck here, title provided by human when they uploaded the image, reflected duck. There's an optional description, there are optional tags. What exact text you use doesn't really make a difference. We tried the different variants. Okay, and once we had this data set, we could run the experiment we wanted to run. X-axis ImageNet, Y-axis distribution shifts. And then you can look at effective robustness, basically, where do the models trained on ImageNet captions end up? Just to orient ourselves, blue line, ImageNet training as before. Here we have YFCC trained clip models, lower accuracy, still on the same linear trend. And then we trained models on ImageNet captions. These are the green hexagons. And the point is that the green hexagons are exactly on the blue line. So you're not getting any robustness from adding text annotations to ImageNet. So language supervision alone does not promote robustness. Good, so this was the top right quadrant. Let's see if we can also go the other way. Let's take a setup where we have robustness, like training on YFCC, and let's take out the text and see if we still have a robust model. So this is what we did. Start out with YFCC. The tricky thing is, well, how do we train on YFCC without using the language annotations? We introduced the following baseline for doing that. Step 1, throw away the text and train a self-supervised representation only on the images in YFCC. We call this, we run SimClear for that. And in principle, this is a good starting point. Now you could use this representation and you fine-tune it on ImageNet, but the catch is we don't want to touch ImageNet, right? We know from part 2 of the talk that fine-tuning can really sort of erase your robustness, or at least messes of your robustness. So we wanted to adapt these models to ImageNet without actual fine-tuning. And in order to do that, we carved out a new ImageNet-like data set out of YFCC. Basically, we did this via substring matches. If a given image, specifically if the text corresponding to a given image contains the term golden retriever, then we take that image and we put it into the golden retriever bin. And if you do that, you get a data set with about 3 million images that correspond to the 1,000 ImageNet classes. We call the subset YFCC hard match. So what we do in step 3 is take our SimClear trained representation from step 1 and fine-tune it on YFCC hard match to get an ImageNet compatible classifier. Cool. And sort of like what we do is basically exactly this experiment. Again, put this on our scatter plots. And here the new point now is the orange diamond, which is YFCC SimClear training plus classification. And the takeaway is that the models trained without CLIP on YFCC get almost the same robustness as the CLIP models. A little bit below the line, maybe good question what's going on there with this last 1 or 2 percentage points. But overall, it's clear that you can get a good amount of effective robustness without the language supervision in YFCC. Cool. So this is why we can take out language supervision here as one of the main causes for CLIP's robustness. We have more experiments in the paper regarding loss function and test time prompting. In the interest of time, I'm going to skip this now. And in the end, the only thing that was left was the training distribution. So while CLIP uses language supervision as a core component, all of the robustness actually comes from the more diverse pre-training data set. Cool. And this then leads to an obvious question: how can we design better pre-training data sets? So this is a paper we wrote last year where we compared how much do different web data sources actually differ in their robustness. How much do the models trained on these data sets differ? And this is a similar story here. We look at our scatter plots for the 4 OOD test sets, and we build models trained on, or we build a test bed of 6 different web data sets: Shutterstock, Wikipedia, Conceptual Captions, Reddit, Lion, and YFCC. And depending on the data set you look at, you see very different robustness trends. I think there are many questions coming out of this paper. How do you combine these data sources in the right way? Another important question, obviously, was how can we operate in the open source machine learning world in a higher accuracy regime? So this is why we built the Lion 5B dataset, because we wanted a large-scale image text dataset. Because it's sort of like a takeaway from this talk that you can already see is sort of like one really important component in all of the exciting recent progress in AI are the large pre-training data sets. So we said CLIP, lots of robustness gains, all from the pre-training data set. And I think the other big advance you've seen from large image text data sets are the fantastic progress in image generation, like DALL-E 2, Imagine, Stable Diffusion, and so on. Like the underlying foundation for all of this is big image text data sets harvested from the web. The Lion 5B is one example. We don't have that much time, so I'm going to go over this a little bit more quickly. It's the largest public image text data set by more than a factor of 50x compared to prior public data sets. And yeah, I mean, there are many details for how we built this exactly. A key takeaway here is that the models trained on Lion do really well. They don't quite do as well as the models trained by OpenAI. So our models trained on Lion, 400 million data points, similar to the CLIP training set, 400 million data points. They are about 3 percentage points worse at the L14 scale. For smaller scale models, the gap is actually smaller. If you look at a B32 model, it's only for 0.4 percentage points. For the larger models, as you make the models larger, Lion seems to scale worse. And on some of the out of distribution data sets like ObjectNet, the gap is also larger, 9 percentage points. So Lion is a fantastic starting point here. But the important question is, how can we build these large pre-training data sets in a better, more principled way? And sort of like as a starting point in this direction, we're currently putting together a benchmark for dataset design, right? So in standard machine learning, dataset is fixed and you innovate on the model side. we are going to turn this around now. We are going to say model training code is fixed, and participants are going to innovate on the data side, for instance, by proposing better data filtering methods that you can apply to a large online crawl like Common Crawl. And we already have some really nice preliminary results. This should be on archive in a couple of weeks. Basically, for training large-scale CLIP models, we get an order of magnitude improvement in training efficiency. So a model that previously took about 500,000 GPU hours to train to 80% zero-shot accuracy on ImageNet, you can train to the same 80% zero-shot accuracy on ImageNet now with only 34,000 GPU hours, because you can train a smaller model for a smaller number of examples. And I think this is just the beginning. I think there's a ton to explore on the training set side. Cool. But for now, let's conclude. So taking a step back, at the beginning of the talk, we highlighted the out-of-distribution challenges in the ImageNet universe, like ObjectNet, ImageNet R, ImageNet V2, ImageNet Sketch. And that the CLIP model made a lot of improvements on these challenging out-of-distribution data sets where no other method was really helping much. And the key question then was, okay, where does CLIP's robustness come from? And it's all from the pre-training data set. It's not that the data set is larger, it's also more diverse in a way that I don't know yet how to quantify more precisely. So I think one very interesting research direction here is how can we measure data set diversity? And just to be clear, while language supervision isn't the key driver of robustness, it's overall still a very, very important innovation. Because I think one of the reasons why OpenAI could put together such a nice, big, diverse data set is because language supervision is very flexible. You can just put together many different data sources from many different places. As long as it's image plus arbitrary text caption, it's the same format and you can train a model on it. And before that, we didn't have that, right? When we were in the more classical supervised ImageNet world, it always had to conform to the same class hierarchy. Cool. And now, as mentioned already before, for me, a really important question now for machine learning is, how do we construct training sets that yield broadly reliable models? I think we have done so much cool work as a community on the model architecture, optimization algorithm, and so on side. I think there's an equal amount of work to be done on the training set side now as well. Yeah, thanks a lot for listening. I'm happy to take questions now, just at the very end. I already mentioned the link to our OpenClip repository for training CLIP models. And if you want to explore our robustness measurements more on robustness.imagenetv2.org, you can browse through all of these scatter plots. So thanks a lot.
Great. Thank you very much, Professor Schmidt. That was very, very, very interesting. So if you have, for the audience, if you have any more questions, just put them on the chat or we can speak up directly.
If there are no more questions now, people are also welcome to email me later. Or you find me in the Discord, in the Lion Discord.
Yeah, I think the last part was pretty heavy, so people are probably still processing it. That's my case, actually. Actually, I had one question. You know, there are many research, a lot of research about domain adaptation, domain generalization techniques that try to mix different data set distributions, etc. I don't know if you evaluate some of these approaches to improve the generalization. And
yeah, that's a great question. So, yeah. So basically, in our robustness evaluation, like the big test bed from the beginning of the talk, we only really looked at zero-shot generalization. So can we take a model that does well on ImageNet and directly apply it to an ImageNet compatible test set like ImageNet V2 or ObjectNet? I think depending on the application, you want either zero-shot generalization or maybe some fine-tuning is okay, or transfer learning. I think there's a great question how much you can improve on these distribution shifts if you allow yourself some amount of data from your target distribution, maybe unsupervised, maybe with labels. I think one concrete challenge of doing this on ImageNet V2 and ObjectNet and so on is that we don't have as much data from these out of distribution test sets because they're only test sets. People like building a training set is a lot more effort than building a test set. So we don't have as much data out of domain there, but you can still try methods that work with small amounts of data. I think it would be very interesting.
Actually, it's just because the fact that Lion is so large that maybe it actually includes the same distribution as ImageNet v2. So that could
yeah. It's a great question. So we are pretty certain that Lion does not actually include ImageNet v2. So it's not that the actual images are included, but you are right. There's a question of like, if you have a more diverse broad distribution, are the models actually doing more extrapolation? And I think a reasonable answer is no. They just see a more diverse training distribution. For me, pragmatically speaking, I want reliable models. I want the numbers to be high on all sorts of data sets. And if a better pre-training data sets give me higher numbers on all sorts of downstream tasks, then I think it's okay if the models don't truly extrapolate, because we don't really know what true extrapolation means. Sort of like humans are obviously pre-trained on like super diverse distributions. So why should we only look at models that are trained on ImageNet?
I see. This makes sense. Any final words, questions? Okay, in that case, I think we can conclude this session. And I would like to thank you again, Ludwig.
Cool, thanks for the invitation.
This very interesting presentation and talk. I'm super familiar with it, and
happy to send you the slides.
To get in touch. Thank you again.
Good.
And
Sounds good. Thanks for staying up in Europe.
So our next talk
Good
will be
night.
done next week. Bye.